Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem, number of steps to reduce a number in binary representation to 1. So I'm actually going to show you two solutions to this problem. The first solution is going to be the less efficient solution. It's going to be an n-squared solution. I will say that this solution conceptually is going to be much easier to understand, but coding it is actually where the complexity is going to come from. The second solution is going to be more efficient. Conceptually, it's going to be a bit more tricky to actually come up with, but in terms of implementing it, it's actually going to be a lot easier. So just keep that in mind. So the idea is we're given a binary string like this, and we want to reduce it down to 1. And the choices we have to do that are actually pretty simple, because either we can divide the number by 2 or we can add 1 to it. And we don't even have to make that choice. There's no decision tree here, actually. The choice is made for us. If the number is odd, we add 1 to it. How do you know if a number is odd? Well, in binary, it's actually really easy. You don't have to mod it or anything. You literally just look at the least significant bit. This is the ones place. If it's a 1, it's odd. Otherwise, it's even. In this case, we will add 1 to this number. And the number we're going to get as a result is going to look like this. Because if you add 1 here, then you carry the 1 and then add it over here. So until you reach a 0, you're going to keep carrying that 1. And then, of course, this will be replaced with a 0. Now, when you have a 0 in the ones place, then it must be an even number. So this is the part where we divide by 2. So now we're left with this number. And I could continue this simulation, but one point I really want to get across to you is that the total number of operations that we're going to do to reduce this number is going to be proportional to n. So what I'm kind of getting at is there's definitely possibly a linear time solution. First of all, let me kind of prove it to you that we definitely can reduce the number in roughly n operations, at most 2 times n operations. Think about the worst possible case. Before we even do that, let's think about the simplest possible case. Let's think about 1 with a bunch of zeros. This is the best case because, okay, we're going to divide by 2, get rid of this, divide by 2, just keep dividing by 2 until we're left with 1, and then we're done. Okay, but we know sometimes we're going to have to add 1. Consider this example here. Now, when we add 1, what we're going to do is add 1 over here. It's going to be changed to a 0. Then we're going to carry the 1 over here. We're going to end up adding a 1 here. And so this is going to turn into a 0, this, and then this. And then we're going to have a 1 over here. And now we're going to divide all of these, and we're left with a 1, 1. And this will be changed to a 1, 0, 0. And then we'll divide this. This is another example, but again, the bottleneck comes from having to sometimes add a 1. Let me now actually show you the worst possible case. This is the worst possible case where we have a single 1 over here you're about to see, because think about it logically. We have, let's say, an even number like 98. We divide it by 2, okay? Worst case, like there's only 2 possibilities. Either it's an odd number or it's an even number. If it's an even number, obviously we're just going to keep dividing it by 2, and maybe it'll just keep being even. That would be the ideal case. That's what I showed you over here. But the other case is, what if it's an odd number? Okay, if it's an odd number, then we'll add 1 to it. Then it's going to become an even number. And then, of course, we can divide it by 2. But again, in the worst case, it's going to turn into an odd number. It's possible that when you divide an even number like 98, it turns into an odd number. If you divide an even number like 100, it can sometimes turn into a even number. Obviously, we know that powers of 2 are the ones that are really easy to keep dividing by 2, as I've kind of showed in this example over here. So when you look at this example, we're going to have to add 1 to it. It's going to turn into this. Like this is going to be a 0, and now we're going to have a 1 over here. And then, of course, we're going to chop off this 0 by dividing it by 2. But once again, now we're going to have to add 1 and turn this into a 0 and put a 1 here, and then divide this. Just keep going. For pretty much every single spot, we'll have to do at most 2 operations. For this example, we'll have to add and then divide. add and then divide, and just keep doing that until we finally get over here. Knowing this, how can we then solve this problem? Well, the easiest way is just to run a simulation on the input. So pretty much, we're going to keep track of what the input string is. Let's consider this example because it's a bit more complicated. We're going to look at the last digit, of course. If it's a 1, we add 1 to it, and then we get the new resulting binary string. It's like this, right? So now we would again look at the last digit. It's a 0, of course. This time we would remove this digit. That's literally exactly what we're going to continue to do. Now we're going to look here. Okay, it's a 1. So let's change this string into this 1, 0, 0. And then again, we'll look here. Okay, it's a 0 now, then delete it. And just continuing this way. And as I kind of proved, even this is going to be a linear time solution, except we know that with strings, manipulating a string is actually an O of n time operation. So that's actually going to make this solution less efficient. Even though we're doing n operations, each operation would be updating the string, which is going to be n squared. And we're also going to be declaring some temporary strings, so the space complexity is also going to be O of n. I'm going to code up this solution first, and I'll show you the more optimal one next. So the idea is we want to count the number of steps. I'm going to call that result, and then we want to return that. How do we know that we're not done yet? Well, we'll just look at the input string and we'll check if it is not equal to what we're looking for, just a single 1, then we're going to continue to go. Now, the simple case is what I'm going to start with. What if the last digit, and in Python, you can get the last digit like this by taking the -1 index and then checking, is this equal to 0? If it is, we just want to chop off the last character. In Python, we can do that like this. It's pretty easy, just like that. Even this, keep in mind, is a linear time operation though. So next, in the else case, we want to change s. We want to add 1 to it. Now that's going to be a decent amount of code. So I'm going to put that in a helper function, which I'm going to call add 1 to this string s, and then return the result and then assign it to this. Now we could have incremented our result here and we could have incremented it here. But if you notice, we're doing it the same way for both times. We're doing a single operation for each. So what I'm actually going to do is just put that incrementing in the while loop portion. So regardless of which one of these we execute, we're going to increment by 1. Now let's go ahead and implement that helper. So I'm going to call it add 1. It's going to take an input string and it's going to return a string as well. So first things first, I'm going to declare a pointer. I'm going to set it to the end of the string because adding 1 to a string is actually not always going to be as easy as I showed in the last drawing example. But if you were watching, I kind of also went over an example that kind of looked like this. We might have, let's say, a few 1s at the end. So if we want to add 1 here, it's going to be a bit more interesting. We know when we add 1 to a string like this, it's going to turn into a string that looks like this. 1, 0, 1, and then zeros. So in other words, we start at the end here. While we have a 1, we're going to keep shifting our pointer. We're going to start here, then we're going to be here, then we're going to be here, and then finally we're going to stop here because that's where the 0 is. That's where the first 0 is. We change that 0 into a 1. And we change all previous characters into zeros. What we're doing is basically turning each of these into a 0, and then finally at the position that we stop at, we turn it into a 1. Now, technically, there is another edge case. Like we could have something like this, a bunch of 1s in a row. What's this going to turn into? It's going to turn into this. Like there isn't a 0 here. That's what I'm getting at. Like we were looking for the first occurring 0, but this time we don't find one. We probably go out of bounds. So this one would turn into this. Like each of these would still be replaced with a 0, but then at the end, we'd put a 1 at the beginning. So there's many ways to code this function up. I'm going to kind of take advantage of Python just to kind of keep this pretty readable. What I'm going to do is we're going to have this pointer, but I'm also going to turn this string into a list. We can do that in Python pretty easily just by calling list on the string. And so now it's going to be an array of characters. The reason I'm doing that is because strings are immutable. We can't modify a string, but we can modify an array. At the end, we can turn it back into a string like this by joining all the characters or all the substrings from it with this as the delimiter. So obviously this function is going to be a linear time function, but we kind of already knew that. Modifying a string is linear time. This is also linear time. Now, just like as I said, while the pointer is in bounds and the current character is equal to a 1, let's change it to a 0. And let's shift our pointer as well. So now at the end, there is a possibility that we could have gone out of bounds. If I is now equal to -1, we went out of bounds. Let's add a 1 to the beginning of this array. A readable way to do that in Python is kind of like this. So this is a array with 1 in it, and we're going to add that with the current array. So this is pretty much just adding a 1 to the beginning of this. Otherwise, we're going to change the current character to a 1. So that would be like this example that I was talking about, 1 0 0 1 1 1. So we would stop over here, we change that to a 1. All the previous ones would be changed to zeros. So all this thing is doing is just updating the string by adding 1 to it. This is the entire code. Let's run it. As you can see on the left, it works. It's somewhat efficient. It is an n-squared solution. It works, it passes, but there's a better solution. Let me show that to you. The idea is going to be the fact that we don't want to modify the input string at all. We don't want to do that at all. And we don't need to do that at all either, actually, because we only care about the current bit, the current position. Remember, we know here we're adding 1 to this spot. And we know that that actually involves two things. That involves adding a 1 obviously here, which is then going to be carried to this spot. And so this will change to a 0. This will change to a 1. And then we want to chop off this 0. And that's going to be one iteration, like our pointer started here. Now we're going to be at this position. And we counted 2 operations that we had to do. And that's always going to be the case when we end up adding a 1, because regardless of what the input looks like, this time it looked like this, the 1 was only carried to this spot. Another example could have been this, where like if we add 1 here, and this will always turn into a 0, but the 1 could be carried pretty far. In this case, it's going to be carried all the way over here. And then all of these are going to be changed to zeros. So the only question is, how do we do that without actually modifying the input? The answer is by keeping track of what the carry happens to be. Kind of the same way you do addition in the first place, right? So it's kind of a math solution. Let's focus on this example over here. Let's see how we can make this work. We know we're adding a 1. So in terms of like counting the total number of operations or steps, initially it's 0, but we know that since this is a 1, we're going to take at least 2 steps now. And so by adding this 1, of course, we get a 0 here, which we know we pretty much delete because our pointer is now going to be over here. That's why we counted 2 steps. But more importantly, the 1 here, like this adds up to 2, right? So a 1 has to be carried to the next spot. There's going to be a 1 over here. So this is now going to be 0. And all these are, but we're not going to be modifying that. So instead of doing all of that, we're going to have a variable called a carry. Initially it was 0. Now it's going to be set to 1. So now when we come to this next spot, we see the value here is a 1. That's where our pointer is right now. It's a 1, but is it really a 1? How do we know? Well, we look at the carry. We take our carry and this digit and add them together. Of course, this is a string, so we will have to convert this to an integer. It's not going to be super difficult, at least in Python. So we take these 2 numbers, add them together. Of course, we're going to get 2, but we know that we're dealing with binary. It should either be a 0 or a 1. So the way to get around that is to take this and mod it by 2. So doing that will give us a 0. So we know that even though there's a 1 here, the true digit here currently with the current state of the string should be a 0. Okay, so anytime we come across a 0, we will shift our pointer. Of course, we're always going to be shifting our pointer, but when we increment steps, we're only going to add 1 this time. Because remember, getting rid of a 0 is going to take 1 step. We're just dividing by 2. Just dividing by 2, and that's a very simple operation to do. What about the carry? Should the carry change? Not really. It should stay a 1. Now when we're here, our carry is again still 1. So we know that the true digit here is actually a 0. So again, we will shift our pointer over here and we will increment steps by 1 once more. And then here, same thing. Now we're going to shift our I pointer to be over here. This is where things are going to get interesting. And the total number of steps we've counted so far is going to be 5, because 2 steps here and then 1 step, 1 step, 1 step. And now we're here. So now we're at 0. Our carry is still technically 1. So that's because here we had two ones, we added them together, we know that's a 2, so therefore we carry the 1. So here we have a 0, but we know that the carry is 1. It was carried all the way from here, all the way here. So this value is actually going to be a 1 bit. What do we do to a 1 bit? Well, we add 1 to it, of course. That's exactly what we're going to do here. So remember, the carry is a 1. So this value is a 1. Now we're adding another 1 to it. So it becomes 2. So now we're going to have another carry. So carry is going to stay 1 here. So now that would mean we're adding 2 steps to the total. So I think the total number of steps is going to be 7 so far. So now our I pointer is going to be here. Remember, this is a 0, but our carry is still 1. So this is a 1. Therefore, we add 1 to it. Again, that is going to be 2 steps, and the carry is going to stay 1. Now our pointer is going to be over here. Total number of steps so far, I think, is 9. I'll kind of add that here so we don't run out of space. We are finally at the last digit. Now, this is the part where shouldn't we stop? We got rid of everything except this over here. So this is where things get kind of tricky. It's easy to make a mistake here. So it's a 1, our carry is 1, therefore the real value here is a 0. Keep that in mind. What that really means is we should get rid of this 0 and then we will be done. That's when we'll truly be done. Now, the easiest way to code this up is just to say that we're going to keep going until we reach this position. Once we reach this position, we're going to stop. If our carry was 0, then we don't have to do anything, right? We're pretty much done. The total number of steps that we counted is complete. If the carry is a 1, though, we will have to add 1 to the result because we know we're not actually just left with a 1, we're left with a 1, 0. That means we have to chop off this 0 over here. So the easiest way to code this up is just to count the total number of steps until we reach this spot and then add the carry to that result. That's pretty much the solution. Everything I showed you is technically correct. And since obviously we didn't modify the input thing, so it's going to be O of n time and constant space. There's just one little detail that's kind of subtle, but it's confusing when you actually think about it. Do you notice that the carry never changes? Once we set it to 1, it never got reset back to 0. You might think when we arrive at a 0 value, shouldn't we reset the carry back down to 0? No, because remember, first of all, when we added the 1s here, then we have a carry. Then we add these 2. And that's technically a 0 spot, right? Like this changes to a 0, this changes to a 0, this changes to a 0, and this is a 1. When we run across a 0, we don't change the carry back to a 0 because then we'd stop carrying it, right? But also, when we reach a 0, we also didn't change the carry because the 0 is not actually a 0. It's actually a 1 because our carry was 1. I know this part is really confusing when you think about it. So maybe the best thing to do is just to not think about it, but there is absolutely a reason that we're not resetting the carry back down to 0. Think of it like this if it's more simple for you. If we have a very trivial example like this, then we don't have to carry anything. All we do is get rid of the zeros. But no matter where we have extra 1s, whether the 1 is over here or it's over here, that 1 is going to end up being carried forever because we have to add 1 to this spot. So this time, we add 1 here, that 1 will end up being carried all the way over here and then end up be over here. The other case would be maybe this is actually just a 0 and then the 1 is somewhere in the middle over here. Doesn't really matter. We chop off these zeros. Once again, we add the 1 here and that 1 is then going to be carried over here. And then we're going to add 1 there, and it's going to be carried over here. And then we're going to add 1 there, and it's going to be carried over here, and then it's going to be carried over here. No matter where we add the 1 will always be carried all the way to the left of the most significant 1. So that's why the carry has to never change. Okay, now finally, let's code it up. First, I'm going to have our result, and that's what we're ultimately going to return, the number of steps. I'm also going to have a variable for the carry. Initially, it's going to be 0. I'm going to have a pointer, which I'm going to set to the last index while, and I guess I actually don't need to do this, so maybe I'll just do this for I in range, length of s plus 1, and then reverse this. So this is basically just iterating in reverse order with a for loop in Python. And I think this time we actually don't need the plus 1 because I think by itself range would be going from 0 up until the length minus 1. And right now we want to do the reverse of that. We want to go from length minus 1 up until 0. So this should be correct. Now we want to get the current digit. Like normally we'd say like if the current spot is equal to either 0 or it's equal to 1. So we could even say this, else if s of I is equal to 1. Or you could just put like an else statement, probably doesn't make a difference. But we know that we're worrying about the carry. So to get the actual digit at this current spot, we have to get the current character and add the carry to it. This is an integer, this is a character, so we have to convert this into an integer first. And also, this could have been 2. So we want to have it either be 0 or 1, so we're going to mod it by 2 just like this. So now we check, is the digit equal to 0 or is the digit equal to 1? This is the simple case. If it's equal to 1, all we do is increment the result by 1. We don't update the carry, we don't touch the carry at all. Otherwise, we will see that the value here is a 1. We're going to add 1 to it, of course, therefore we're now going to have a carry. And this time we don't increment the result by 1, we increment it by 2. So this is almost the entire code. Can you think of the one thing I'm missing? I did talk about it in the drawing explanation. It's down here. When we return the result, we actually do still need to add the carry to it. So this is the entire solution. Let's run it to make sure that it works. Okay, actually I had a very, very subtle bug and I'm sorry about that. Remember, we want to stop when we get to the first index. When we get to the first position in the string, we want to stop. So therefore, we don't want to iterate on the last iteration of this loop. So actually, I'm going to make this range be a 1 through this, and it will be iterated in reverse order. So we're going to go through this, and then 1 will be the last iteration of the loop. When we get to 0, we will stop. And unfortunately, there's one more issue. I'm not sure what's wrong with me. I'm pretty sure I said we're going to be incrementing the result by 2 on this condition. For some reason, I still had a 1 there. Sorry about that. As you can see on the left, this solution works and it's definitely more efficient. I'm pretty sure if I just run it one more time, it will indicate that. Yeah, so now it's 80% more efficient. So yeah, that kind of shows you that these runtimes are pretty random. If you found this helpful though, check out Leetcode.io. It has a lot more. Thanks for watching and I'll see you soon.